Well, here we are. Now we have so much data, lots of images, lots of text. We have more data than we know what to do with it, right? And luckily, we have deep learning models with lots of parameters, lots of layers, performance improvements across a wide range of tasks, right? So everyone seems to be happy, and maybe I should stop the talk right here and spare you an hour, right? But there are troubling trends as well, right? So we have seen repeatedly that many of the good models, they have been very brittle with respect to small changes. You take an instance and give it to a system which is used to, like you give it to a system that is used to these kind of instances, things are working fine. I make small changes, for example, very simple contraction, and things dramatically fall apart. And more broadly, what I'm gonna focus on in this talk is driven by the observation that majority of the success that we have had recently in the field, they have been on the problems with abundant data. And there is little progress on tasks, on domains, when we don't have a lot of annotated data, right? And this is problematic because in natural language, we will always have settings where we do not have enough annotated data. And this happens because in natural language, we always have domain changes, context changes, style changes. And all of these factors, they go hand in hand, and they create a vast space of possibilities for how language could be interpreted and adds on top of its complexity. To give you an example, think about this conversation that you could have with your futuristic assistant. Right? For example, you ask your system, show me a bunch of restaurants nearby. And it gives you a bunch of options. So far, so good, because we have really good retrieval systems that can give you good candidates with respect to simple queries like this. But let's say somehow I remember that I want to specify an extra condition. For example, I say, I'm allergic to peanuts, right? You humans, you understand how to respond with respect to this query because you have an understanding of what peanut allergy is and how you should react to this. But for a robot, for a machine, it's not really clear how we can really teach it how to deal with these kind of situations. In fact, I tried this on my iPhone, and what it did was exactly opposite of what it was supposed to do. It gave me a suggestion to go to a restaurant which serves peanuts, right? Exactly the reverse, right? Now the issue is, if you want to design a system that learns to deal with these kind of situations, how would you go about teaching this? Would you annotate a data set of conversation that focus on peanut allergy? And if so, is it going to scale? Because I can easily change this response to some other condition, some other scenario, which completely changes the way you have to reply to this specific situation. So overall, what I'm arguing in this talk is, it is unlikely that we will have directly annotated data that covers all the aspects and complexities of natural language. However, there will always be weak signals. There will always be hints that we can exploit, use, in order to solve problems and do something interesting with that, right? To channel a little bit of symbolism here, what we have seen in the field is we have been riding the wave of annotated data. But if your goal is to explore the whole ocean, it's not really clear you can rely on these kind of waves to get anywhere. And in particular, in this talk, I'm going to focus on parts of this ocean where we do not have much waves. Right? Just to be clear, I'm distinguishing between supervision and data. When I talk about supervision, I'm talking about pairs of inputs and outputs. Think about it as a collection of documents annotated with some labels. When I'm talking about data, this is what you should think about. A bunch of, let's say, text, documents, possibly not structured, and freely available information, for example, Wikipedia. One is minimal, scarce. This is direct annotation. And one is abundant, right? So in this talk, I'm going to talk about two very distinct and different problems: answering natural language questions and semantic typing of natural language entities. These two problems are very different, but what ties them together in this talk is the way I'm going to try to address them. And I'm going to study them in the settings where I have minimal supervision, minimal annotated data. Although I have minimal annotated data, I'm allowed to use other resources. Like I can go to the web, I can use freely available representations, I can use Wikipedia, I can use something about the structure and definition of the problem, I can use the compositionality that is inherent to natural language. Right? And finally, I'm going to end the talk with a brief discussion of a few things that I'm excited about. All right, so let's start with the first section. Well, just a heads up, this section is heavily inspired by the kind of things that I did a couple of years ago here in AI2. So it might be very familiar to some of you, but hopefully it won't be very boring because there will be spices once in a while. Okay, well, let's begin from the very beginning. Why do we even answer questions? Well, the grand goal for us here in NLP is to equip machines to understand a given text just like how humans do, right? So this is what we name it as NLU, natural language understanding. And to get to this goal, this broad and general goal, we need ways to measure our progress, right? And answering natural language questions about that given text is basically one way of measuring our progress. Basically, if a system that has a better understanding of natural language should have a better chance, higher chance of answering questions about it. This is something that is almost as old as AI itself and has been studied under many different definitions and settings. Right? And in particular, in this talk, we are going to focus on the data set that Peter has introduced a couple of years ago. Natural language questions of elementary school science exams. Here's an example. A bear survives winters with what structure? And given this, in addition to this, we have a bunch of candidates. And we are also given a paragraph. It's unseen, but there is a paragraph that potentially gives us some hints about the answer of this question. And these questions are written by humans, and they're targeted for humans too. They're targeted for kids. And the language is very simple. But it might be misleading because for machines, the challenge here is to understand what is given in the text, abstract over all these events, entities, and do something interesting, some reasoning on top of that abstraction, right? So it might look very simple, but it's not as simple for machines. Let's take a closer look into this. In a perfect world, the evidence that is given to me is very simple, right? So for example, here in this hypothetical case, it's almost a part of the question and part of the correct answer. In this case, I can just do a simple word matching and boom, I'll get the answer. But life is not always simple. In reality, what you get is something like this. Polar bears, saved from the bitter cold by their thick fur, are among the animals in danger of extinction because of global warming and human activities, and a couple of dots. The point here is that language is variable. A single meaning can be mentioned in many different ways. And if you want to create a system, a natural language understanding system, it has to be ready to deal with the variability in natural language. And this is not just the whole evidence. This is part of a much bigger paragraph, which talks about, in general, something about these polar bears, right? And your system has to discover where is the right sentence and what part of it answers the given query. How do usually people deal with this? Well, an easy solution here is supervised learning algorithm. I have an input, I know what my output should be, I take a data set of these pairs, and I train my supervised learning on a collection of such pairs. This is what I call a direct supervision. Right? And these systems, indeed, they have been very, very successful. They have shown some really impressive results on certain data sets that usually with lots of annotations. But things can break down as well. So for example, this is particular instance, if you run it through Allen NLP demo, it's actually going to give you this span as the correct answer, right? I tried this yesterday. So things can break down. But the issue is not about who gets it right, who gets it wrong. That's not the issue. The issue is, now that we made this mistake, can we really do something about it? Can I go into the model and figure out where did things go wrong? And even beyond this, how can I fix my system? and let's say, would you be able to annotate a collection of QA pairs that focus on polar bears in order to fix this? Is that a solution? It might work, but is it going to scale? That's the question. So in this talk, what I'm going to try to show you is something that has two major components. We are going to try to present, create a representation of knowledge. And on top of that, we are going to create a reasoning system. The representation has to have some form of structure, but it shouldn't be too rigid, too specific. And the reasoning has to be effective and general on top of that. Right? This is the big picture. Right? And then let's start with knowledge representation and take a closer look at the instance that we were just looking at. Well, we have to notice that verbs are important in conveying meaning in natural language. And sometimes we have to be able to infer that some verbs, they convey similar information. Propositions, important. They convey really informative information about their arguments. Commas, they sometimes convey some interesting properties in natural language. And in order to understand this, answer this specific instance, you have to be able to understand something about each of these single phenomena. Right? So really what I'm arguing here is, in order to solve QA, you have to understand each of these single phenomena. Really, QA is a natural language understanding problem. Right? Let's take a closer look at these phenomena. So luckily for us, the field over the years has really focused on each of these individual phenomena. For example, if I want to understand what this by means here, I can go to the toolbox that the field has provided, for example, proposition semantic roles. And this system, or these kinds of systems, they will tell me that this is expressing an action that is done by an agent, right? So it lifts the meaning in the form of some semantic representation. You can think about it as a graph, a small, tiny little graph, right? This abstraction, this lifting of the meaning, this might look very simple, but it is not. In fact, in order to show this, I can change something about this text. For example, I can change by their thick fur coats, I can change it to a different string. For example, I can change it to by the river, and the meaning is going to change. In this case, the meaning changes to an action done in a certain location, right? Two different meanings with a small change, right? So in fact, if you look up in Oxford Dictionary, there are 8 different meanings for the proposition by. So what the system does under the hood is it disambiguates the meaning that is expressed by natural language, right? So we do some form of disambiguation here. You can do something similar again with other tools that are provided in the field. I can use my comma semantic role labeling in order to understand that here I'm dealing with an apposition structure. There's a description about a given mention. Again, there are many different ways that comma can convey meaning, and this is only one way. I can do something similar. I can have, for example, I don't know what happened. I can use verb semantic rules in order to understand that here survivor of what is the survivor of this incident is a bear, and the adverse circumstance from which this bear is being survived is a winter, and what structure is something that is missing, and that's what I should look for, right? And I can extract this kind of graphical representation of the meaning using verb semantic rules, right? And putting all these together, I create this basically some form of semantic representation of given natural language instance, right? This is what I get. Just to be clear, this is a representation of only a subset of the instance. Like the question, as I showed you, the paragraph is much longer. I'm just showing you much smaller, much simplified representation just to convey the point, right? And now, to give you the big picture, we show the semantic representation or the meaning of a natural language in the forms of basically a collection of semantic subgraphs. The semantic subgraphs that are provided by the tools that are already exist in the field. They have developed independent of question answering. The graph structure, they convey some meaning about the event in that locality in the text, what that meaning expresses. And the nodes here, they express some representation of that given span. Its surface form, its role in that subgraph, and some your arbitrary, your favorite representation. So the point here is that the meaning is represented by a collection of tools or semantic representations that are independent of the task that I want to solve. And because of this independence, I expect this representation to be more broad and more general. I expect it to be easier to generalize across different domains and tasks. Moving towards the solution in terms of how I want to answer this specific QA instance, the idea here is that we're going to create some connections between different moving pieces of this instance. And I'm going to create, and we are going to do this by something that I like to call a support graph. A support graph is something that connects different pieces of my representation together, and finally it connects it to one of the candidate answers. This subgraph has to be able to connect the parts of the instance that are almost equivalent or entailing, and form a reasoning, a sensible reasoning on top of what is given to me. Or to show you the big picture, given one QA instance, we create a representation of all the meaning that is given here. Right? And doing question answering here is basically finding the best support graph on top of these graphical representations. One graph can be this, one graph can be this, and your job is to basically find the best graph or best explanation that answers this given question. If you're familiar with the classical AI literature, this is something that traditionally been studied under abductive reasoning, finding the best explanation given the information that is given to you. Right? To give you an overview of the framework, the key design challenge here is designing this box, the model builder, which takes in the question, the semantic representation of your input, and some black box that tells you whether different components, different spans of text are almost equivalent or entailing. For example, it can tell you that a bear is an animal. Right? And given these inputs, what you get is an optimization problem as a function of your inputs, which in this case, we formalize it as an integer linear program, as an ILP, right? Which, if you're not familiar with, which I think most of you are, it's optimization over a bunch of binary variables with linear objective, with constraint with a bunch of linear inequalities. And given this optimization problem, you can give it to an industrial ILP solver, and hopefully in the output of this, you're going to end up with a support graph that explains, that answers your given instance, and it gives you a correct answer plus some scores, right? So this is basically the big picture. And the rest of the rest of this section is basically dedicated to how we are going to approach building such block. Or another way of looking at this is, where are the sources of the knowledge here encoded in this big picture? And if I want to point out the sources of knowledge, part of the knowledge is coming from the semantic representation of the text. Part of my linguistic knowledge is coming from how I combine, how I connect local notes, phrases, and how I'm going to connect these different moving pieces and create a reasoning, a support graph on top of it. It's encoded in my optimization problem, right? Before I tell you how we do this, let's first talk about the challenges. Well, we want to formalize this extraction of support graph in terms of that optimization problem. And we have to be careful about many moving pieces. We have to be ready, and we have to make sure that this optimization is going to be able to simulate all the possible reasonings that you can do across different range of questions, right? It has to be very flexible. You have to make sure that you score better connections, stronger connections. You have to be ready to deal with spurious connections, misleading information, and you have to make sure that you get an optimization problem that is going to scale up. Very briefly, you have to define three components. You have to define what are my variables, what do they represent, what your objective is, and what your constraint is. Variables, they encode whether a given edge or node is part of my support graph or not. For example, you have a variable for this, you have a variable for each of these single nodes. And altogether, they collectively define a space of all the possible support graphs. Your objective function encodes the intuition that you want to give more weight to those proofs, to those explanations that have better support. Like you want to give more weight to stronger connections, well-supported arguments, and you want to penalize your system for weaker connections, for spurious connections. Unlike objective, which tells you about preferences, constraints tell you about hard requirements. Some requirements are global. For example, you want to have a connection that is connected, and some of them are local. You want to make sure that in local level, you have connections that are sensible. For example, if you are using a verb semantic rule, a predicate argument structure, you want to always make sure that you use its predicate along with its arguments. Right? So, and by now, you should have some form of understanding of how this framework works, and which means that it is time for showing some evaluation. Well, the first system that we are going to compare with is Peter Clark's information retrieval system, which is indexed on lots of freely available text. The system is actually compatible with the point that I was making earlier, not using supervised data. So in that sense, I give it a green light. This system, this is tuple inference. This is Tushar's system, which does inference or sort of multi-hop reasoning on top of automatically extracted OpenIE tuples, combined with a bunch of first-order logic rules. And here we have neural networks, which is again developed here. We have BiDAF, right? First, let's compare it with, let's look at the results on 4th grade exams. Here we have IR, we have Tushar's tuple inference, we have Minju's BiDAF, and this is what we get. And if you go to 8th grade exams, you see a similar trend. Basically, what we see is, very briefly, ignoring many moving parts and details, semantic ILP, or what we develop here, it beats the baselines by a couple of percents. Yeah?
Do you have any idea of the overlap between the correct predictions for BiDAF and the semantic ILP? Are they like, I want to know what the like overlap of the Venn diagram is.
In the paper, we have overlap analysis between this and this. But that can be a good thing to explore. Yeah. I'm going to add an extra twist. Oh, yeah, sorry.
Do you have any intuition of why IR works better than BiDAF or inference model or the educated exam?
I think Peter Clark might have better intuition here.
I think probably the difference here is sort of small. They're both performing approximately the same.
Okay.
The two others are using supervision.
Free text, almost free text. It does use supervision. It is fine-tuned on the data set. Minimal supervision. Okay, yeah.
How large are these data sets?
This is then public data set, which is around 300 or 400 instances. Okay. I don't know what I'm doing here, but okay. Well, I'm gonna add an extra twist here, and I'm gonna evaluate the same system on a different data set. I'm gonna evaluate on biology exams, which have questions like this. What does meiosis directly produce? A bunch of candidate answers. So same kind of structure, but in terms of vocabulary, in terms of what they ask for, is very, very different. These are the questions that are relatively technical. And now the question is, if we take the same system and if we move it to this different domain, is it really gonna generalize? Right? Are we just creating something for science exams, or there's a bigger, more general finding here? Right? And what we see here is, well, I'm going to evaluate on IR, I'm going to evaluate on BiDAF. ProRead is an expert system within this domain. It is defined and constructed particularly for this domain, right? And if we look closer into the results, we see that what we create here is it gets something relatively close to the domain expert. So I think what we are getting here is something more general. We successfully generalized to this domain. let me try to wrap up what we saw here. Well, I argued that in natural language in natural language, we have to deal with collection of semantic phenomena. It's not just one single thing. There are a collection of semantic phenomena, and in order to deal with this, we have to be able to have some form of representations that capture different parts of this natural language phenomena, right? So it's not just one piece. There are many different complexities that have to be dealt with. And in order to do this, we took what the field has done over the years and we put them together. I argued that this is indirect supervision because these tools, these semantic representations, are developed independent of the task that we solved here. And by creating a reasoning system on top of that representation, we showed generalization across different domains.
When you compose the ILP problems, there are a lot of potentially moving pieces that you could better fine-tune,
Yeah.
quote unquote fine-tune
Yeah.
for a particular domain. Could you maybe make some comments about how that can be done in a principled way?
I think it is important to note that even this system that we create, it is not parameter free. There are always parameters that you have to tune with. But I think the main point here is that 50 parameters is much less than a couple of 100 million parameters, and likely easier to tune and more likely probably you're not going to overfit on that, right? So it's definitely a research challenge. I don't think I have a straightforward answer as to what is an effective way to tune those parameters. For us, it has been a process of an expert looking at the predictions on just a few instances and moving the parameters slightly to see whether you do something more meaningful or not. Yeah.
Because I just wanted to add that for the context that we didn't mention is that this was like work done years I have to do when all our Aristo data sets and of this kind were much smaller and BERT and such didn't exist. Now we know BERT, trends and everything can get up to like 70+% on these. But this was at the time at least like better than any other solver we had across all our systems, all of our data sets. Thanks, have changed a little bit.
Yeah, things changing really fast.
Sorry.
Yeah.
Another question. So your motivation of this graph thing is really to provide more kind of better explanation on trying to actually answer questions in a more correct way. And but I haven't seen you show any example of like is it really doing what you intended to do, or
Okay.
it just actually help you to get better?
Yeah, that's a good point. I think for me, being able to explain it for the right reason, writing codes, at least in this talk, it was sort of secondary. My focus was really not relying on direct supervision. In our experiences, sometimes, as you would expect, things can go wrong. Like you answer things, but not always for the right reason. But at least you can open the box and see that, oh shoot, this is really happening, right? There's an explicit explanation. So yes, maybe we should have done more on that. Yeah.
Do you have a sense of like what part of the process is the bottleneck? So, for instance, if you had, say, you did develop the question answering data set on top of the onto-nodes corpus,
Yeah.
where you have essentially gold semantic graphs, right?
Yeah.
Do you think you would get like 90% question answering performance, or like what's the bottleneck? Is the bottleneck not having gold semantic representations of the graphs, or is it the ILP part, the reasoning part?
I think there are a lot of moving parts here. One is, one can actually challenge me by saying that how do you know that you have an exhaustive semantic representation of all the possible phenomena that can happen in a QA system, right? So that's something that we haven't really discussed.
Yeah.
Another thing is you have to be able to really, this entailment component that I had in order to combine these together, that was really a local chain. It's not really clear that those decisions that are made in local level, they tell you something more meaningful in a global level when I want to do multi-hop reasoning. I think there are a lot of moving pieces that can go wrong here. I think I gave 2 instances, but I think that's more open-ended discussion. Yeah.
So going back to hand-tuning the ILP parameters,
Yeah. Uh,
on the science something? The non-Aristo data set, did you tune the parameters separately?
there is some hand tuning, right? Of course, on the training data, not on your test set. But I think the main point here is not whether tune or not. The point is you run the same system without changing it across two different data sets.
Mhm.
That's the main point. Yeah.
A different way to ask Mark's question is, what is the performance of the various components that you use, like which were predefined in the existing work, to build those representations? What is the performance of those systems? Is it like
Oh,
70%
on this-
or 100%? Yeah.
On this particular domain,
On this or a related data set?
I'm not sure about that. Yeah. Because we don't have gold annotation of those representations on this particular domain. So Mark was trying to take QA to the domain where I have gold annotation.
Yeah.
Now you're saying that what is the performance of your semantic rule on this data set? I'm not sure about that.
What is the performance of those systems on the data set that they evaluated on?
So I see that some people here, people who have developed semantic rule labeling, they're not here. It's definitely above 80%, I would say, but things can fall apart when you go to different domain, not sure, yeah. Okay, so let's move to the second part of the technical section of the talk, and where I'm going to talk about semantic typing of natural language entities. A very different problem from the other problem that I talked about in the first part, but what's going to ties this to the story that I'm talking here is the methodology, is the way I'm going to try to solve this. Right? Let's start from the beginning. What is this problem? Well, there's a text, the context, a bunch of mentions are indicated, and the goal is to attach some semantic type to each mention in the text. UW, I have to be able to understand that in this context, not only an organization, but also an educational institute. Why do we do this? One motivation here is dealing with ambiguity. Here I'm showing you 3 different sentences. They all mention Paris. Our break in Paris was quite memorable. In this sentence, Paris refers to city. I met a girl named Paris. In this sentence, Paris refers to a person. Paris issued a statement condemning the proposal. Paris, in this case, it refers to government. And if I have a semantic entity typing system that can attach each mention of the Paris to each of these types, it basically disambiguates the meaning of the Paris in each of these contexts. Another motivation for doing semantic entity typing is gaining generalization by creating abstractions. And let me explain this by giving you an example. The question, let's take this question, which month receives the most hours of daylight in Paris? Let's say you have a good system which tells you the answer is June. What does it take for this system to be able to deal with the perturbations of this question? For example, if I change Paris to Seattle, what should this system really know in order to understand that this answer to the same question is, again, June? And you can think about it as basically a semantic entity typing problem. So the system has to be able to understand that Paris and Seattle, they're both of the same type, they're both cities in Northern Hemisphere. And again, if I make different changes to this question, if I change it to Melbourne, the system should understand that, again, this is a city, but it is a city in Southern Hemisphere, and it should connect us to December. So this is generalization by doing abstraction on top of natural language. What is the state of the field on this problem? If you look at the collection of the data sets that people have developed over the years, we have all sorts of definitions for typing. We have coarse typing with relatively small number of the types. We have fine typing with many more types. And you can actually add an extra axis of domain here. Most of these are in the news domain. There are many other data sets that are developed for biology and law that I'm not going to mention. But so basically the point is there are many different ways that you can define this task with different type definition. What is one way that you can, what is an easy way of solving this? Take this sentence. A former Democrat, Bloomberg switched his party registration in 2001. One easy thing that you can do is you can map mention of Bloomberg via entity linking systems to the page that expresses Bloomberg. And you can use resources like Freebase to map this page to a bunch of types that are expressed by this concept. Well, this is good, and in fact, it is sort of compatible with the first argument that I had, because it doesn't really use any dataset-specific supervision. But the problem here is that the problem here is that the types that I get, they're not really compatible with the context that is expressing this specific mention. And in fact, if instead of Bloomberg, if I had a nominal mention, let's say if instead of this I had Jack, the system would not be able to map it to a given concept. So it wouldn't work if the concept is not really available in Wikipedia. So instead of this, what people have done over the years is they choose their favorite supervised learning algorithm, and they train it with a bunch of with pairs of inputs and outputs on a particular data set, and this becomes their entity typing system. The problem here is that as soon as you train the system on a particular data set, it is fixed and limited to that particular collection of types, right? So you cannot really take it and evaluate it. You cannot take it to a different data set. It is limited. Instead of this, what we're going to do, we are going to replace this box with our own system, Zoe. Right? And again, Zoe is a Sesame Street character, which stands for zero-shot open entity typing. In addition to the traditional input, Zoe also takes in an extra input, the definition of the types that you're interested in. And according to this definition, it gives you a type. You can actually change this input, your target taxonomy, and the Zoe is going to give you an updated collection of types. Right? So it is open because it is not fixed to a fixed collection of types. It is zero-shot because we are not going to use task-specific, dataset-specific supervision in order to create this. Right? How do we approach building such system? The idea is that we are going to associate some semantics with what really a type means. And we are going to type this as a conceptual container that contains a bunch of concepts. Right? So I know what politician means as a type because I've seen instances of a politician. I know what company means because I've seen instances of the company, right? But in fact, if there wasn't any company in the world, it wouldn't make sense to have this as a type, right? So this is defined by these. And if you give me a sentence like this, the idea is that I'm going to look for concepts in which that appear in a similar context compared to the given instance, right? Just to give you an example of this. Given this input, I'm going to go through the contexts in which any of these concepts of known type, they appear. For example, I might come across a sentence like this that describes Elizabeth Warren. Warren is a member of the Democratic Party after switching party affiliation from Republican Party in '96. Many people didn't know this. And you can do this because there are resources like WikiLinks. They're available independent of the task that we are solving here. And you can use tools like Elmo to recognize that these two contexts, dimensions in the context, they almost convey a similar point. Right? And if you do this, you can map this. And if you have enough of these kind of contexts, you can, with some level of confidence, you can map it to a politician. Now, if I give you a different sentence, since its founding, Bloomberg has made several acquisitions. Again, I can go to the context in which any of these concepts appear. And I might find a sentence like this about Berkshire Hathaway, which says it says something about its acquisition. Again, I can use some context consistency with Elmo and decide that this is of type company. Right? So what we did here was using using context consistency as a proxy for typing entities in their context. To give you the big picture, given an input, we map it to a collection of concepts that are sort of context consistent with your given input. And with a little bit of post-processing, some information aggregation, we infer a bunch of types. If you want to think about it in terms of resources that are used, there are many things that we are using here. We are using Wikipedia, we are using Elmo, and so on. Right? And none of these resources are really restricted to the data set that you are solving. These are really freely available resources that are out there for you to use, independent of the task. Time for a little bit of evaluation. Here, I'm going to evaluate the systems on fine typing of entities. And I'm going to show results on 3 different data sets. Figer dataset, BBN dataset, and Antonot dataset. 3 completely different data sets with different collection of types. If I look at the best systems that exist for a Figer dataset, the best systems really get really good scores on this particular dataset. But I have no way of transferring these to other datasets because the type definitions are completely different. In a similar way, I have the scores of the best systems on this particular dataset, but they don't generalize to other datasets. And similar thing for the Antonos dataset. But Zoe gives you performance, gives you something on each of these datasets at the cost of, once in a while, at the cost of losing a little bit of performance. Right? So you gain generalization at the cost of a little bit of performance. Let me try to wrap up this section. Well, what I showed here was an approach, one way to deal with, to solve natural language and semantic entity typing. And in order to, without reliance on direct supervision. And in order to do this, we did a little bit of reformulation. We defined what really type means. And by using this reformulation, I created a system that shows better ability to generalize across different taxonomies and domains. All right, so really, to take a few steps back, what I argued here in the introduction is it's unlikely that we will have enough annotated data that capture all the peculiarities in natural language. Creating annotation is hard. There are many difficulties here. And really, in fact, we don't even know what all the tasks in natural language are. There are going to be some tasks in future that we are not really aware of. And it is really important for us to go beyond the paradigms that we currently have, beyond supervised learning. Right? And what I showed here were just 2 instances of how we did this by effective user representation and reasoning on top of that. Right? And I want to emphasize that these 2 instances, these are not just 2 systems. These are 2 initial steps of a bigger picture. Right? So I think there's a bigger picture here. Which brings me to the final part of this talk, which is I'm going to give you a little bit of something, a big picture and what I'm excited about. If I want to define myself, most of my work has been dedicated to natural language processing. And on the side, I've also contributed to machine learning. Within natural language processing, one can describe my contributions in terms of some sub-areas like semantics or doing some reasoning on top of those semantics. And on the side, I've dedicated some time to make sure that we make these the product of the research available in the form of tools and resources to the community to have some form of impact. Right? And to follow this direction, one of the things that I'm really excited about, and I think many of you are also excited about, is the advent of language models. So basically, we have created these systems that go to lots of freely available data. They absorb some patterns, and we somehow use it in order to improve our systems. I want to emphasize that these models are actually compatible with the philosophy that I described here, which is being able to go to freely available data, use it in order to improve your existing system. So there's no contradiction here. In fact, they're mutually reinforcing, right? And I think the field has looked at these systems in a narrow sense. Most of the times we use these as like in terms of features, along with our supervised learning algorithm. We go back to the old paradigm. But I think what really fascinates me here is that we can really issue explicit queries to these systems and really look into what they understand and what they don't. For example, I can say Spokane is some empty space, largest populated city in Washington, and the system can give me some distribution over what it thinks I should put here. So in this case, it gives me the correct answer. It's not always about good facts, good information. There are a lot of things that is missing. And really, in order to effectively use these kind of systems, I think one has to dedicate good amounts of time to understand what is the nature of the knowledge that is encoded within these systems. And after understanding this, we have to find mechanisms to decide whether something really is known or not known. What is it that I know exactly? I want to automate this process. And after doing this, you can do some form of inference on top of the knowledge, the kind of frameworks that I talked about in the technical part of the talk. Right? And since we are talking about knowledge, we can also extend it and talk about the problematic aspects of knowledge. I can talk about, for example, bias that is encoded in my language model. I can talk about the wrong information, misleading information that are encoded here, conspiracy theories. And after discovering these, I can talk about how I can mitigate these kind of problematic information. And speaking of conspiracy theories, I want to go back to the big picture and add a new box here. And this box is something that I like to call information pollution. This is not only an application of all these different technical areas, but it is something that's going to introduce new problems and drive the research in each of these technical parts. Right? And the final part of my talk is going to be explaining why I think this is an important and interesting problem. Right? Let me take you a couple of decades ago. When information technology started, it started with so much hope and positivity. We thought that information technology is going to increase the democracy, it's going to help many people have better and easier access to information, and it's going to make the world a better place. What happened was something completely different. We ended up with so much information, many of which are irrelevant, redundant, unsolicited, incorrect. And this resulted in really radicalizing effects. Right? So you have seen this in US election, you have seen it in Brexit. It's not just about politics. Every single day, many people go to web, lots of medical forums, and search for queries like, what is the best treatment for something? What are the side effects of something? And as micro users of information, none of us know whether people who are providing this information, do they have an agenda? Are these information that I'm reading, are they consistent? Are they false? Are they misleading? Right? And it's not just about checking what is factual and not, what is factual and what is not. Many of the important problems that we are dealing with, they don't have a simple answer because you can think about them in many different ways. Should animal testing be legalized or not? You can argue for or against it by using different arguments, and depending on the context, on your background, both of them might actually make sense. Right? So it's not just about checking what is factual and what's not factual. Calling this problem fact-checking or fake news is an oversimplification of the challenge. So to connect this to what I started with natural language processing, I think there are two different angles that we can really have some effective contributions here. One, understanding of the sources. I want to be able to understand who should I believe, who should I trust, who has agenda, who is misleading me, and so on. And I have to be able to understand evidences. What evidences are false, what is true, what evidences are contradictory, what evidences are mutually reinforcing, and which ones are sort of orthogonal, right? And these are not only our applications for natural language processing, but they also derive the research in what we do basically as a pure research. We took the first step towards this in our NACL paper. And in this paper, what we do is we want to provide users with an understanding that the world is not really black and white. There are many aspects to a single problem. If a given system, as I show it here, is supposed to take in a given claim and look up from a given pool of perspectives, it is supposed to look up a bunch of perspectives that address this issue and tell you whether these issues are supporting or they're against this given claim, right? And by creating systems like this, we hope that people are going to be more willing to see the other side of the other side of the aisle, basically more open-minded about listening other people that they do not disagree with, right? Let me try to summarize this. Suffering from information pollution is not something that we have to live with. We are not going to go back in history. Time is not going to go back. We have to find solutions for this problem. And in particular, natural language processing, plus some algorithmic tools, is going to be part of the solution. It's not just computer science. We have to also go to other communities, policy, social sciences, and also bring them together here in order to create more collaborations for this problem. And connecting this to the story that I started with, a lot of problems here are really nuanced. You can't really create an annotated data set in order to deal with this problem with this scale. In fact, there are many issues in a society that we don't even know what they're going to be. They're just going to happen in future. You can't really create annotated data for that, right? And I think it is a really interesting challenge. It is important, and I think hopefully over time this will result in societal impacts. And with that, I want to give credit to my incredible co-authors. A few of them, they're here. And many of them, they're actually not there. But thanks for being here. And